Hey, welcome back to another physics lesson on, this time we're going to be looking at properties of fluids. Now, fluids are pretty cool. They're a little different than solid. So solid is definitely not going to flow, but liquids, and so here's your liquid right here, and then gases, and this is kind of how I draw gases, they're going to be able to flow, which means that we have this little concept that is going to change depending on where you are in the fluid or how much fluid is around you, and that is called pressure. We've been talking a lot about energy and as energy moves through a system. Well, work and energy can be defined in fluids as we look at the idea of pressure. Because what is pressure? Well, pressure is simply, if you have a flat surface, it is basically the amount of force that's exerted by the particles onto that surface, and it's a perpendicular force. We assume that it's straight on like this. Now, why is that important? Well, you may have heard of things like, let's say you got the diver, and and you may have done this. You're diving down underwater. Here's your air bubbles, boop, 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 and you feel this pressure on your ears, right? It hurts really, really bad. Well, what is that? Well, it's because the force of the water molecules above you are pushing harder on your eardrums than the air inside your ear is pushing out. So your eardrums are starting to have a net pressure pushing them in from the outside, and that hurts. And so you could force some air inside there, that equalizes it out, and you can dive deeper, and divers learn how to do that. Or you may have learned how, if they're really, really deep, they can't just come up to the surface. They have to stop and do what we call decompression, right? And now why is that? Well, the pressure of the force of the fluid above them is actually keeping the oxygen in their blood liquid. And if they go up too fast, they don't have that pressure, and the oxygen's going to turn into gas bubbles, and then they're going to have bubbly blood, and they don't want that. You never want your blood to boil real bad. That's also going to happen in space. You go into space. Yeah, here we are in space. Here's the stars around. If you're just up in space all of a sudden, well, your blood would actually boil. Why? Because you don't have the pressure of the whole atmosphere on top of you. Thank God for all that pressure that is pushing down on us, because that actually keeps our blood in its liquid state and keeps those molecules together. So pressure is extremely important. In fact, the pressure of the atmosphere above us is what allows airplanes to fly. This is what an airplane looks like. There's the propeller in front. And it allows an airplane to fly. You thought maybe it was the wind produced by the propeller. No, that's just going to give it some speed. It's actually the pressure difference over the top of the wing versus underneath. So how does a force perpendicular to the airplane make it go up? That's kind of weird. Well, we will learn about that as we get into this. Now, let's think about another concept right here. If here you are, if I throw a big old brick at you, and let's say this brick weighs 40 kilograms, right? And I throw it at you, ow, it's going to hurt. But will it pierce the skin? Probably not. But if I throw a dart at you, here's my dart, boop, 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 with a sharp needle point, is that going to pierce the skin? Yep, it's going to pierce the skin. It's going to stick right through it. Well, why is that? What's the difference? Is there more force on the end of the dart? No. This brick falling through the air would have way more force than this little needle. So why can the needle pierce the skin but not the brick? Well, the difference is going to be surface area. If you look at the little tiny surface area of the end of this needle, it's extremely small. So all of this force is going to be applied only over this tiny little surface area. It's going to be able to pierce right through your skin. But this brick has all this surface area that all the force is going to be applied onto yourself. So pressure is measured. Oops, I'm going to go ahead and rewrite that. Pressure is measured as the force divided by the surface area, right? So the smaller the surface area, since that's the denominator, the higher the pressure, right? And so you don't need a whole lot of force if you have an extremely small surface area to do something like pierce your skin. Okay, now let's get rid of all this junk. I drew a box here for you. Exciting. And let's say that this box is 20 centimeters by, let's say this is 10 centimeters and this is 5 centimeters. Let's say the box is solid lead. Lead has a density of 11.8 grams per cubic centimeter. All right, so the question is, which part, if this lead brick was dropping through the air, which side, if you could choose a side, which side would have more pressure? Which side would actually hurt more and do more damage? Well, the answer, of course, is the smaller side, because it has a smaller surface area. It's going to give it a higher pressure. So let's go ahead and figure out some calculations. We learned that pressure equals force divided by surface area, right? Now, pressure is measured in units called a pascal. Actually, it's just PA right here. And so a pascal is actually the force of 1 Newton per square meter. Okay, and so that's a single pascal. Okay, so what we have here is we have centimeters, and so for us to convert this into pascals, we might have to do some conversions right here. And we don't really have a force yet. We know it's dropping through the air, and we know that we have a density. So what do we need for figuring out the actual force of this brick? Well, we're going to need the force of gravity, right? Which equals mass times g. Oops, g right there. So how do we figure out the mass from the density? Well, density equals mass times volume. No, I'm sorry. Density equals mass divided by volume. So actually, mass equals density times volume. And so this would be something that we could do. We could figure out this, do some conversions right here. Now, what do we want? We want either to convert this mass into kilograms, or we would want to convert this volume into cubic meters. Let's go ahead and just solve this and figure out this mass in kilograms, and then multiply it times the acceleration of gravity, which works on kilograms, 9.80 meters per second squared. That's the acceleration of gravity. So if we knew the mass in kilograms, and we know this, we could actually figure out the force. All right, so let's go ahead and do that. So the force here is going to be, let's see, what's going to be the mass? So the mass is going to be 11.8 times my volume, which is going to be 20 times 10 times 5. So that's actually 1,000. So this is going to be pretty easy. So what I'm going to end up doing is multiplying this times 1,000, and then to convert it to kilograms, right? 1 kilogram equals 1,000 grams, because remember this density was initially in grams right here. So so I'm going to basically divide by 1,000. So at the end of the day, I come right back to my same answer, saying that this mass is going to be 11.8 kilograms. So 11.8 kilograms times my force of gravity, 9.80. Let's go ahead and figure that out. And that's going to equal 1.20. Oops, I did that wrong. Sorry, I did not multiply. I accidentally divided. Okay, so, oops, sorry about that. And not quite sure why that happened. And that's going to equal, let's see, what did I calculate that out to? 100, so this time I didn't divide, 0.64. So this is force. So so right here, this is 100.64 newtons. So we have centimeters. So we have 50 square centimeters. And we want to convert this to meters, because remember, a pascal is a newton per square meter. So in order to get this into pascals, we need to convert this to meters. So square centimeters to square meters, we're going to basically be dividing by 100 twice, right? Because this is centimeters to meters would be 100 two times, so it's going to equal 0.005 square meters. So if I go ahead and divide this out, 0.0005 square meters, I'm going to get 23,128 pascals. So since these are usually big numbers, what we usually try to do is convert this to kilopascals. So it's actually going to equal 23 kilopascals, and that's kind of more of the more accepted way to do it. Now you can see that if you were to go ahead and use this right here, then it would just be 115.64 newtons. That was our force right there, and we'd be dividing by instead of 0.005, we'd have 200 centimeters. And we divide by 100 times, so it would be 0.02. So 115.64 divided by 0.02 is going to give us 5,782 pascals. That's if we were to get hit with this side, which equals 5.8 kilopascals. So you can see that the difference between the pressure on this side and the difference between the pressure on this side is a big deal. We got 5.8 versus 23 kilopascals. So clearly pressure has a lot to do with surface area, and it'll change greatly just the two different sides of a brick that would hit something. So in the next video, we're going to look at a couple different examples of pressure changes in atmosphere and those kind of really awesome things, so stay tuned.